In lesson 17, we'll be talking about collinearity or multicollinearity, and we're going to be talking about how we detect it and some of the implications that can arise when there is collinearity between our regressors. This lesson is going to be focused on just motivating what it is, talking about the definition, some early signs of multicollinearity, and then talking about the tools. And the next lesson, lesson 17b, will really focus on using those tools. What do those tools mean? How do we interpret? So let's get started. Our motivating example is this air quality control example. In this example, let's assume that we want to understand some health index. This is going to be our response in relation to different air pollutants that could affect health. Let's say our predictors are sulfur dioxide and soot. Now, we know that sulfur dioxide may have a certain effect on the health that soot doesn't. But we also know that these might interact with each other. And so we want to be able to see and detect if sulfur dioxide has an effect. Okay. In the ideal experiment, we would be able to examine a whole range of sulfur dioxide levels and a whole range of soot levels. What I mean by that is in this picture, we would be able to get low levels and high levels of soot. We would also be able to get low levels and high levels of sulfur dioxide. However, this is not realistic. Realistically, pollutants tend to be produced together. And so in this example, typically when soot is low, we also have a low sulfur dioxide. Also, when we observe high soot, then we would observe a high sulfur dioxide. So they have this relationship together, and we aren't able to get this. Again, remember, we're in an observational study, and there's no way, at least to my knowledge, on how you can control having low soot and high sulfur dioxide when we're just observing data. So multicollinearity or collinearity focuses on how the X's are related to each other. There's nothing to do with the Y or the response. And so we want to understand if some of our predictors or regressors in our model are highly correlated. There are some implications, and why this would be bad is because when there's multicollinearity, we can have unstable estimates of our betas. And this would cause be very dramatic from one experiment to the other, or when we're choosing our models. So for instance, if we have our slope for our partial slope for the sulfur dioxide vary dramatically from one observation period to another under certain conditions, or from the model with or without soot. Okay, so we can have unstable estimates. Then if our estimates are unstable, then our interpretation of those can be very difficult. So if you recall back in lesson 13, our typical interpretation of the beta is the mean response will increase with 1 unit in the predictor when we hold all the other predictors fixed. This may not make the most sense when multicollinearity exists because the two variables are working together, okay? And we can't necessarily hold the soot level fixed. What I mean by that is, that's why I haven't changed the notes yet, is typically when we were looking at the betas for one of our regressors, let's say it's the sulfur dioxide, we were able to hold soot constant at this low level and then be able to look at the sulfur dioxide. But now in this case, we have no data up here. And so it's harder for us to make that type of interpretation. Just so you guys see where I'm at. Some of the early signs of multicollinearity are changes in your estimates of beta when a predictor is added or deleted. So you'll start seeing these really big jumps in your betas. Another issue is a wrong sign for your estimate. So let's say in our example, we get a beta or our partial slope for soot that corresponds to having a high soot index, which indicates a healthier index. We wouldn't expect that. We would typically expect our beta to represent, if there's a high soot index, then there's a lower health, our health index is lower, we would expect that. So if your beta signs aren't making sense in respect to your problem, then that's another sign of multicollinearity. What happens a lot of time is when we have multicollinearity between our predictors, it's going to result in a lot of variability. And so that's why we're going to get these large changes, or we're going to get our signs positive or negative that don't make sense. Another thing that can happen is an insignificant result in the individual tests or the partial tests on beta of an important predictor. So what I mean by this is that we run our linear regression and we look at the overall left test, and the overall left test tells us, hey, it's significant. There are variables in here that will help us understand our response. But then when you look at the partial regressions, you see all of them are insignificant. So it's kind of contradicting itself. That could be another sign of multicollinearity. Some of the tools that we're going to be looking at in our next lesson are going to be looking at scatter plots of the predictors against each other. Again, this is going to be just the X values. We're also going to be looking at correlation between predictors, and we'll focus some time with variance inflation factors, also called VIF. And then we'll very briefly talk about condition indices portions of variation, very briefly, more just as, hey, here's an extra little tool for you guys if you need it.